Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we'll continue with more on thermodynamic assessment. Today we'll focus on thermodynamic models. These are going to be the contents. We'll focus on how Gibbs energy is modeled based on types of phases, and then we'll focus on first unary systems and then binary and higher order, where we will first see solutions. This is something that we have seen in the introduction to computational thermodynamics just before the hands-on sessions. And today we will focus more on need for a better modeling framework, and we will look at sublattice formalism, and using that how intermetallic phases and even solutions again can be modeled in this framework rather than the method that we have seen before. Okay. This outline is possibly there in your mind now. What we are going to focus now on is on this particular part, modeling. And models depend on types of phases. Okay, in phases, the solid, liquid, gas are there. In solid, we have a random phases. Random in the sense the chemical order is not there. In that we have two types, substitutional and interstitial. Substitutional solid solution and interstitial solid solutions. Then there are phases which have chemical order. We call them long range order, LRO. And in that we have these two different types, non-stoichiometric and stoichiometric, whether there is one single composition and a range of composition. Then in liquid we have a completely random, and then there is something called short range order. This is also a chemical order, and this occurs in some of the liquids. We'll see how to model them as well. You may recall what we have seen for unary Gibbs energy model, where we have splitted the model into different contributions like this: G lattice plus G physical plus G pressure. This G lattice is without any physical contribution such as magnetism. For example, if you look at the Cp versus T for an element like iron, you will have Cp without magnetism like this, and the moment magnetism is added, it's going to look very different. And this has to be modeled separately and added, and that's how we add this G physical term. And if there is a contribution due to pressure, then we have to add that separately. Remember that. And this is what we said. For Gibbs energy of lattice, we can use Mayer-Kelly polynomial, and for the physical contribution magnetic ordering, we will use Inden-Hillard-Joule model, and for pressure, Murnaghan model. You can go back to some 7 lectures back to see the equations of these things. Okay, the first one we have seen this random chemically disordered phase. For example, substitutional solid solution SSS, which has no chemical order. For example, copper NaFCC solid solution. How we modeled it? We modeled it using this kind of equation, where we have this reference energy, which is pure element Gibbs energy at the mechanical mixture Gibbs energy. Whichever reference state we consider for that, based on that we calculate this term G reference plus delta G mix ideal will anyways be there. This is the ideal mixing tendency, the tendency to mix the elements randomly, and this term arises from that, which is basically delta S ideal mix multiplied by minus T. We have seen that. Then the excess Gibbs energy, this is the most important part and difficult to model. This is where we use this kind of composition and temperature dependency terms, where LAB comes. Its LAB is called as model parameters as function of temperature and composition, and we expressed it using Redlich-Kister power series. And in the Redlich-Kister power series, we had these different LAB terms coming. We can add as many of them as possible. For example, in this figure, this white line is the actual Gibbs energy of the phase, excess Gibbs energy, and that can be modeled using 3 different L parameters. Addition of all the 3 will give this particular Gibbs energy of the phase. In that case, we have 3 different L parameters. Accordingly, there will be different composition dependencies coming here. Xa minus xb power 0, 1 and 2 will be multiplied with this term, and xa xb will be anyway multiplied with all of them. So this is how the model we saw for a substitutional solid solution phase. And this model parameters LAB will have this kind of temperature dependency V1 plus V2T plus V3T LNT and so on, where this V1, V2, V3 are called coefficients of model parameters. Okay, these coefficients will have a slightly different name when we do the thermodynamic assessment. They are called as variables. In thermocalc software, we will use this software, and in that, especially the parrot module, we'll be using this is PARROT. I'm sorry for the spelling. In that, V1, V2, V3 are called as variables and not coefficients. Okay, right. Now there is a need for better framework for modeling. What is that we are talking about? Okay, a symmetric delta G mix requires only one L parameter. More L parameters represent more complex composition dependencies. So we have seen this. So more L parameters are required to represent a complex excess Gibbs energy like this. Now, if this goes into any shape, accordingly we have to find a different number of LAB parameters, add them so that we can get the actual Gibbs energy. Looks straightforward, but there are multiple problems. We'll see them one by one. It seems RK power series is good enough to model any shape of GX curve, but if the curves get too, let's say, deep only at certain compositions, okay, so let's say something like sharp V, okay, RK power series may require many L parameters. It may become not easy to handle. So that is a problem. And then there are more reasons to go for a better modeling framework. Phases with a long range order, the chemical order, let's say stoichiometric compound, something like AB. Okay, it has a B2 structure, let's say. For example, ALNA. Of course, ALNA is not strictly a stoichiometric compound, although it's non-stoichiometric. Let's proceed with this example at the following composition, which is XB is equal to 0.5. Okay, let's say mole fraction is 0.5 and it's a AB type compound. Two elements are there in B2 structure. Okay, you can see here NaAl. We have seen this picture. Two different sublattices like this. You can imagine this to be two separate nickel and aluminum sublattices interpenetrating into each other. Okay, creating this kind of a ordered structure in two dimension. Nickel, aluminum, and so on. Right? You remember this. Now this is what we are talking about as long range chemical order. This can be considered to have two interpenetrated sublattices of simple cubic structure, one with aluminum and the other with nickel, right? And how to model it. See, why we are asking this question how to model it now is because we need to get this information that it is an ordered phase, long range chemical order is there in this phase. How do we get that? Okay, name of the phase, let's call it AB in the model. And if this happens to be like this is the excess Gibbs energy of AB and this is for the BCC, some other phase, let's say. So compared to these two, you can see AB is lower. So obviously in Gibbs energy competition, this phase is going to become stable. Now what we need is this Gibbs energy values which should come from this equation for AB's Gibbs energy model, Gibbs energy description, right? Is that enough? Is that enough to tell that this AB phase is having long range chemical order? That's the problem. Okay. So we can, by the right model parameters, RK power series can describe the Gibbs energy of the phase named AB. It can do that. But can it do this? Can it inform that the phase with the name AB is a chemically ordered phase? Answer is no. Okay. It only has the equation and the equation will give these numbers, different Gibbs energy values. Okay. So can a model capture this physical feature? The answer is yes. We can still use RK power series, but within the sublattice formalism, we have to go for a different modeling formalism. We will see what is that. So I can actually start with what is a formalism and gradually build on sublattice formalism, explain what is it, define what is it, and then apply it to some compound like this. Okay, I can do that. But what I'm going to do is directly apply it to this so that you get a feel for what is the sublattice formalism, and then we will slowly define what is that and a little later. Okay. So let's focus on this compound AB and composition is this. And sublattice formalism for AB phase is going to be like this. Two sublattices with equal relative number of lattice sites. This subscript here is the relative number of lattice sites, and the things in the bracket, this is one sublattice, this is another sublattice. So A is in one sublattice, B is in one sublattice. This is basically giving something like a formula for this particular compound, but it is not so. It has more nuances to that. As we go to different compounds rather than AB, you will see that this gets quite complex. Okay, in this case it is quite straightforward. All A atoms in one sublattice, all B atoms in one sublattice, and this is going to be imposed. Okay. Right. One sublattice has constituent of only A and the other has only B. So by the right sublattice formalism, something like this, along with the right model parameters in RK power series, the Gibbs energy of the phase named AB is described along with the information on chemical order. Okay. Even now we can get the Gibbs energy curve for this phase. But if you see, if this AB phase becomes the lowest in the Gibbs energy landscape, then you will not only see AB as the stable phase in the output. If you can look at the information about the phase, and you can understand that it is having sublattices, and in each sublattice you can see the composition and understand that it is a chemically ordered phase. So that information comes as an additional output. How to see it in the results? Okay, let's do a small calculation and do that. We can make a ALNA phase diagram using nickel demo database, and then check single point results at single phase regions BCC B2. There will be one region like that. I will check the results there, and various FCC L12 phases. These things also we will check for this particular detail called constitution. Now the term constitution here is used specifically to refer to sublattices, so it could have been called as sublattices itself, but constitution term is used, but we have used this constitution term in a much broader way. Constitutional data for us means what is there, what constitutes a material, what are the phases inside, what is their chemical composition, what is their phase fraction, things like that. Okay, so that particular thing is not used here directly in that meaning. So constitution here means what is the sublattice information. Based on this we can decide whether a phase is ordered or disordered. So check which are ordered or disordered directly. If we use console mode, it appears after this list condition syntax. Okay, we can do that and check. So after opening Thermocalc, I am opening this file. This file is a macro file that I have generated some time ago for plotting ALNA phase diagram using nickel demo. So you can understand the syntaxes. When I type go data, I go to TC by default FE demo database. From there I can switch to nickel demo database, where I can define system, aluminum and nickel. These two elements are there in this database. That's why we are using this. Then type get to retrieve the data. Then go to poly module, where you can set condition, pressure, number of moles, temperature and nickel content. These values are within the diagram that we are looking for. That's all. Then compute equilibrium. Single point equilibrium is done. Then set axis variable 1 is going to be mole fraction of nickel, varying from 0 to 1. Set axis variable 2 is temperature, varying from 298 to 2000. Then type map. Once mapping is over, go to post module PO. There set diagram axis, mole percent of nickel and temperature in degrees Celsius. Okay. Then plot and set interactive. So this is what we have done there. So there are two ways to run this. Either you can open Thermocalc, type M to call the macro file and call this file wherever it is located. Or you can simply Control A, select all these syntaxes, then copy them and open Thermocalc and simply paste them. Yeah, so now we got a phase diagram, aluminum nickel phase diagram. Let us open it. You can see here BCC B2 phase is in the middle, BCC B2 hash 2 is written. So this phase, if we click somewhere near 50-50, okay, any temperature is fine. Right click, add label. Okay, BCC B2 is stable there, and in the bottom click show details. This is basically we are checking single point equilibrium at a point where we right clicked. Okay, the temperature there is this much, 529 Kelvin around. Okay, composition is 0.5 mole fraction of aluminum, almost 0.5 mole fraction of nickel, both are near 0.5, right? So now in the results we have to check constitution information. You can see here composition is given here for stable phase, only one phase, and this composition, if you change it to constitution here, constitution, click that. Okay, then if you come down, you will see this constitution information where 3 sublattices you can see. In fact, vacancy is given as species in one more sublattice. This we have not considered for B2 phase, the AL-NI phase or the AB phase that we have just modeled. But in this case, vacancy is added as one more sublattice. This is to incorporate more functionalities like addition of interstitial sites or calculation of entropy and things like that. Here, sublattice 1 is having nickel. Site fraction is more like mole fraction of a particular sublattice. Okay, so in this sublattice, almost 1, meaning complete mole fraction, goes to nickel. Okay, so we'll understand this site fraction in next few slides, but understand this right now as the mole fraction. Okay, so mole fraction within a sublattice. So now Al, Ni, Va, aluminum, nickel, vacancy, all three are there in this sublattice. In that, nickel is almost completely there in this sublattice. 0.99 is nickel. Okay, so other two are almost not there. So it is purely nickel that is there in this sublattice. Then sublattice 2, aluminum is 1, other two are not there. Okay, 10 power minus 12, 10 power minus 11 is almost not there. Nickel and vanadium are not there. Aluminum is 1. Okay, so what you sense here is nickel is 1 in one sublattice, aluminum is 1 in the other sublattice. It means two different sublattices of two different compositions. That itself tells you that these are different sublattices. If this sublattice and this sublattice both have same site fractions of elements, it means the sublattices are not different. What we want is one sublattice which is full of nickel, or at least nickel dominant. The other sublattice, it should be full of aluminum. When these two things come together, that's where we form AL-NI type of chemically ordered compounds. And that thing is now happening. From this we can understand that. But if two sublattices have same chemistry, one is also having aluminum nickel equally, other one is also having aluminum nickel equally, it is more like having no chemical order. Even if these two interpenetrate, it's almost like aluminum nickel are equally distributed anywhere. They can sit in any lattice sites. So that means that is chemically disordered. Okay, so checking the sublattices will give us the information about whether a particular phase is chemically ordered or not. Right, so this is BCC-B2. You can also see here FCC-L12-2 here, and here FCC-L12-2. So this region is Na3Al phase actually, that is having FCC-L12 structure. If I right click, add label and show details, within that phase what we see is this. If I go to constitution, I will have three different sublattices are there. If you remove this vacancy, these two sublattices, one is dominant in nickel, the other one is dominant in aluminum. Okay, so this is in Na3Al kind of phase. So 3 Ni, that is 0.75, and 0.25, 1 Al, 3:1 ratio you can see here. Sublattices have some more mixing and all coming here, but we will see about that little later. You can imagine this to be completely nickel and this to be completely aluminum as of now. So that is Na3Al, and you can see that in the site fractions as well, right? So in this case, both sublattices are having two different compositions. Now if I right click somewhere here, this is pure nickel, mole percent of nickel is 100 here, right? So this is pure nickel, and this region is nickel rich solid solution. In nickel, aluminum is dissolving, so this should be a substitutional solid solution, right? There should not be any chemical order here, right? So if I right click and add label, it is still labeled as FCC-L12. It should be FCC-A1. L12 stands for chemically ordered, but it is still labeled as FCC-L12. The reason is there is something called modeling ordered phase and disordered phase, which look like FCC together into one model. Okay, so FCC order disorder model we call it. The name for the entire model will be 1. Therefore, the disordered phase also will be named as the disordered phase will also carry the name of the ordered phase. Okay, so this FCC L12 is there. So click show details. Click show details. What you see is here, and if you go to constitution, this is what you find. Okay, nickel 0.917, aluminum 0.082. Sublattice 2 also nickel 0.917, aluminum 0.082. So both sublattices have same chemistry. It means this is a chemically disordered phase. There is no particular preference for an element in a particular sublattice. So that is not there. Therefore, this is a chemically disordered phase. Right. Okay, this is how you understand different regions. This is a disordered phase. This is a ordered phase of FCC like structure. This is a BCC like structured ordered phase, BCC B2. Okay, you can understand that. This you can check. You can do the single point equilibrium at where you get these different single phases, and do the list condition and check this particular terms displaying in the results, ordered and disordered. This will be displayed in the results itself, in the window itself. You can see that. Now let's see something fundamental about sublattice formalism. Sublattice formalism is a modeling framework. It can be used to model chemical order in phases, homogeneity range of ordered phases, also the random type phases. So if it can order, it can be used to model chemically ordered and ordered phase with some homogeneity range, non-stoichiometric, and random type phases, in the sense that solid solutions and even liquids. If all of them can be modeled, then this can be used for everything, even for solutions. What we have seen initially for solutions is without any sublattices. We just said this is a solution phase, this is a chemistry, this is a Gibbs energy. We just used the RK power series to describe that. Here we are saying sublattices can be put even for solutions. So we are going to use this sublattice formalism everywhere, even for solutions. So RK power series is used within this sublattice formalism to model the phases. Right. So now what is this formalism word means? This should have been my first introduction slide about sublattice formalism. I am putting it here because now you understand what is this. So the sentences I put here will make much better sense. A physical feature can be modeled by a logical framework or mathematical expression called formalism. Okay. And the same formalism can be used to model another physical feature. We said this formalism can be used, in the previous slide we said it can be used for stoichiometric phases, non-stoichiometric phases, and solutions as well. Okay, so for multiple things, the multiple physical features, if the same formalism can be used, and that is where it becomes more powerful than the physical feature itself. It means that a formalism is more general than the physical features. For example, this one, chemical reactions are written in a formalism of reactant 1 plus reactant 2 plus any number of reactants on the left hand side. You put plus marks between them and the Gibbs symbol comes here. Then you have product 1, product 2 and so on, right? So this is the formalism. This captures several aspects of the reaction, right? One, number of products and reactants. Then what are the products, what name and stoichiometry of product and reactants. And also we can put balancing aspects. So here how many number of moles of one reactant is there, is it balanced, we check that, right? So that is mass balance aspect, that is also there. And the direction of reaction, all these things are captured in this framework, right? And this framework, this is a logical framework, it can be used to write any reactions. So this is where the framework becomes more powerful and general to represent so many different things. So sublattice formalism is one such thing. There are multiple terms in it. Constituents, constituent fraction or site fraction, relative number of lattice sites, constituent array, in members, and this name called compound energy formalism. We will see all of them in the next class. Thank you. I hope the lecture is useful. See you in the next class.